Thanks, Tom. So, before I start with the talk, I want to say something. I want to, first of all, tell you we have a Twitter feed about the symposium. So if you're on Twitter, feel free to go there and like things. But the more important thing, he's leaving. I want to thank Tom, because I know our name is on the schedule, but really Tom did the heavy lifting. And he really did a lot of work and a great work. So thanks, Tom. So with that, it's going to be a short talk because Mayor basically covered everything I had to say. So let's see. Oops, what happened? So the future of signal processing is... OK, so maybe I'll say what I was thinking about this talk. What I wanted to do is when Al asked me to talk a bit about new mathematics and new signal process that will come and be important in signal processing, I thought maybe if I was a grad student and I wanted someone to give me a few new directions on what I could start now and look going forward, and maybe going far out into the future of what could be important in the field, what would that be? And what I wanted to do is start with my definition of signal processing, or one definition of signal processing. I know that there's going to be a panel to debate that definition later, but the way I see signal processing is there is an input, and we manipulate that input to make the output useful. Okay? And useful in that definition contains sufficient information so that we can do the next step, the next processing task, easier. Now, what some information theorists and signal processing will say, well, there's the data processing inequality, so you cannot add information in the processing, and I agree with that. So what I'm going to say further in the definition is that what we want to do at the output is have the output in a representation that makes things easier to use. It's not just having the information, but having it in a way that is easy to use. And processing, and that's considering the next stage. And processing can expose or remove information to help the next stage in that processing. Okay, so let's start with a certain example. First of all, let's talk a bit about the data processing inequality to understand what I'm talking about. Typically, you'll have something that you care about that you measure in some input. Let's say you have X and you measure through the input Y, and that goes to the processor, and you have an output Z. And you want to make some inference or some understanding and some decisions, theta, about X. And what the data processing inequality says is that the mutual information between Y and X is always greater than the mutual information, or equal to the mutual information between Z and X. Or in other words, the conditional entropy of X given Y is smaller than X given Z. So what that means is that my processing, no matter what I do, I cannot add information, and whatever reasoning I do about X, it's better to do it on Y, the optimal reasoning. It's better to do it on Y than doing it on Z. The problem, though, is this keyword, optimal. Typically, next stages are not optimal. If you look at a neural network, for example, these days, the last stage is a linear stage. Typical stages are not optimal, and what I want to do is talk about processing that makes this output good for that next stage, which is not optimal. Okay? So let me give you an example. Let's say the next stage is human perception. Okay? So you have a signal that goes in, it goes in the processor, and what you need to do is you want to either display it or listen to it through things. These are things that they used in World War I, by the way. And you want to manipulate the input in order to condition the output such that the human perception can see that better. Okay? Your eyes and ears, turns out, are great low-pass filters, and they're also very good artifact detectors. So you want to, basically, you don't care that much about noise, and you can filter out noise, and that's something that we've used a lot in terms of error diffusion, half-toning, sigma-delta conversion, and more recently, Tom with Lumi, they've been using that with similar ideas to do glassless, very flat 3D displays. And the core there is perceptual metrics and perceptual understanding, which also has become very important in audio-visual compression and things like that. So I think understanding perception, which is something that I can't say we understand very well. I think it's going to be a very important part in the next steps in signal processing. Because we all know how to minimize mean squared error, but we don't know how to minimize eyeball error, right? Okay, now, as I said before, a very common case other than perception is that the next step is a linear step, or it is a convex processing step. And the key goal here is to modify nonlinear and non-convex behavior to expose information so that these systems can use it, okay? And what I want to talk about is first exposing that information. What are some nice tricks that have come up recently and are very interesting in terms of exposing information at a later stage? So one trick that has been done for a very long time, but there are some new techniques in that, is what's called lifting. Lifting the signal to a higher space. You have a signal in a low-dimensional space, and what you do is you try to map that signal to a higher dimensional space, so as I said, so that you make the next processing, the next step, much easier. And kernel methods are a great example of that these are not new methods. We've used that. People have used that in Volterra series estimation. Feature extraction is another example. What has happened more recently is we've tried to lift signals to expose second and higher order structure. And this is an example here. Let's say you have an operation which is linear in x, linear in y, but includes the product of the two in some form, either through a kernel or something like that. And what you want to do is you want to optimize and determine both x and y, but they have a nonlinear relationship between them. They have a product term there. Well, one technique that has become very promising and has already some very good results is to take the outer product of those, lift them in a high-dimensional space, and create an object that is their outer product. It also has some additional structure. It has a rank 1 structure because you took that outer product. And it turns out that this operation, this A, is actually a linear map on the product. So what you can do now is you can use linear techniques and linear methods, including methods that estimate this in a convex optimization or in some kind of linear estimation, as long as you're able to impose that structure on X, which we know how to do, we know from compressed sensing, and make it a rank 1 object. So there's a lot of work on that. The problem here is that the dimensionality now becomes the product of dimensionality. So there is a drawback. It's not don't get things for free. But these days, computing and memory is cheaper. So maybe you can afford that trade-off, okay? And this is a very active area of work. It's very useful in a number of problems, like phase retrieval. Yonina has done some great work there. Blind convolution and things like that. There are a lot of open questions. And one of the big ones is, as I said, reducing complexity. Okay. Next thing is another nice trick, involves nonlinear dynamical systems. And we've seen a lot of nonlinear dynamical systems, and they're pretty difficult to work with. You have a state, and then there's a nonlinear step that evolves the state according to a nonlinear function. It turns out, and that was very surprising to me when I first found about it, there is this thing called the Koopman operator. And the Koopman operator works on functionals of the state, which are called observables. In many ways, it's like a hidden Markov model, which works linearly on probabilities. If you take your system, lift it to that space of the Koopman operator, it turns out that time evolution of the Koopman operator is always linear, even if your underlying system is nonlinear. So this is a very interesting development. Actually, I have to say, it's a very old development. It's just now people realize that they can do that. The main drawback is that, and the catch, is that this operator is an infinite dimensional. Okay? So, you gain something and you lose something. You lose in the fact that it is an infinite dimensional, and you have to approximate. So the key choice here is how do you design and how do you pick the basis functions so that you can have a finite approximation of this infinite dimensional object and still have good performance with a linear system. And this is something we have applied for airflow sensing from limited measurements. Airflow in a room is a very nonlinear dynamical system. But you also sometimes can apply to things that you don't know the underlying equations. We know the underlying equations when we have airflow, but you might have people going through a crowd, or you might have vehicles moving in a video, and analyzing those video sequences with the Koopman operator. You can use linear techniques to do very, very interesting stuff, like estimate different flows, segment the crowd, and so on. It's a very, very interesting concept. And as I said, it's a very powerful framework. Our understanding is still developing. So getting those basis functions, this is something signal processors are very good at. And this is something I think is a very promising area of work. OK. Another thing I want to say, which kind of Meir stole my thunder, is that we all know noise is a problem and should be avoided. But I want to run an experiment. I want to take an image, and I want to threshold it. So I'm going to take, let's say, the midpoint of the intensity and threshold it. And what you see is you get a binary image. It's a pretty good image, but you've missed a lot of the features. You've missed the tower, the green building, and the MIT, the dome, and so on. And then the experiment I'm going to do is I'm going to add noise. And I'm going to keep increasing the noise. I'll add a bit more noise. The image gets a bit better. As I add noise, that image becomes nicer and nicer, both perceptually and in terms of the information content. Okay? And of course, I can overdo it. Right? There is a point where I added too much noise. My point is that intentional randomness, which is something we, again, don't completely understand, we have a good handle in certain cases, but it is known to improve performance in a number of cases. So we know that it can improve the robustness in estimation. We can provide regularization in learning, dithering quantization, as Meir mentioned. Compressed sensing exploits randomness, and matrix conditioning, it can provide that. There's an area of work that some people in Al's group worked in the past, stochastic resonance, that I think is also very interesting. And noise, and intentional noise can be very useful if we can properly harvest its power. And that can be very helpful even later with, there are chips now that can sense very, very high resolution, but very low bit rate, like very few bits per pixel, maybe 1 bit per pixel. If we can exploit the noise there, we can get much better pictures. OK? Next thing, again, Meir mentioned that. Why do we like complex numbers? I guess, if you come from Al's lineage, you have the same ideas, right? It's amazing. Why do we like complex numbers? Well, we like complex numbers because complex algebra introduces additional algebraic structure. It provides easy bookkeeping. For example, it provides an amplification and a rotation. And guess what I'm going to talk about next? Any guess? Quaternions. There you go. 4 parameters in quaternions. They're great at describing 3D rotations. They're great for quantum states and quantum computing. Octonions is the next level up. You have 8 parameters. And there's a more general thing, which I kind of looked at in my PhD thesis. I didn't go that way, but I never left it, because I think it's extremely interesting. Clifford algebras. Who has heard here Clifford algebras? Yeah, I thought so. It's a very interesting a set of algebras. It turns out quaternions, octonions, complex numbers are all subsets of Clifford algebras. They give you amazing structure, and so far the problem was computing and memory. And I think now we're getting to the point where these can be much more practical. So understanding how they work and how they can help signal processing, I think, is very important. And one thing they do is provide structure for reversible operations. I don't know if you noticed from Ike's talk, reversible operations are a big part of quantum systems. And what happens is, if you have an input and you have a reversible operation, you know that the output contains all the information, because you can always go back. And it turns out that in quantum computing and these kinds of fields, preserving the information end-to-end gives you a guarantee that at the end you can do an optimal transformation and get what you're after. So for example, quantum computers implement that kind of invertible transformation. Another area which I think is very important, I've done a lot of work on it, and I think it's extremely interesting, and it's way underexplored in the field, is embeddings. And we know embeddings have played a role in compressed sensing. They're basically transformations that preserve distances. So you go from one space to another, usually easier and hopefully easier to work with, and you preserve the distance and the geometry of the space. And there are a lot of randomized constructions, Johnson-Lindner-Strauss, restricted isometry property, manifold embeddings. There's a lot of work on that. But I think one property of the embeddings that is not really appreciated is that this distance preservation essentially guarantees invertibility. Okay, so an embedding preserves information at a much lower cost. And you know something is important if it has an ology paper about it. So there is an embeddology paper. This is about in some sense, more precise embeddings, but it turns out that with very good use of randomness, as I mentioned before, you can get very good approximate embeddings. Okay? Now, as I said in the talk, there is exposing information, but also removing information. And I think that's very important if your system that you have at the end cannot handle too much information. So let's say you have a detector or a classifier or a Rich's neural network that wants to detect cats. You pass cats that are rotated in that classifier. You need to find the signal. If the signal is rotated, you might get the wrong answer. Okay? And now that's a problem. So what do? You panic. But what you can do is you can change your systems. Your systems are not optimal in the sense to ignore the extra information, which is the rotation of the cat. So what you do is you can use mappings that are invariant to transformation, and there are many ways to design those mappings or even learn those mappings. And they have an interesting connection also with embeddings. So I'll give you two examples of those mappings. You can do shift invariant embeddings, which take signals and then does the embedding, produces a lower dimensional signal, and then you just need to compute an L2 distance, and it produces a shift invariant cross-correlation, minimized cross-correlation distance at the output. And this is very good for shift invariant comparisons. There's also the scattering transform that Stefan Mallah has been, and his team has been proposing as an alternative to neural networks that has different kinds of invariants and have been shown to perform almost as well as neural networks that require extensive training. This is just designed from basic wavelets. Okay? Embeddings can also provide the distance distortion. So distorting the geometry of the signal hides large distances, can hide certain distances, but often helps processing. So large distances, in many cases, in machine learning or in inference problems, can confuse the cost because they weigh so much on the cost that impede inference. They dominate the cost. So the kernel trick is essentially a distance distortion. But as I said, you can use embedding and enable very general distance distortion with much lower dimensionality. Okay? So I'm not going to go into details because Tom is up there with the science. Some final thoughts. Signal processing methods are there to manipulate information, exposing or removing parts in the output. And then the main idea is to allow subsequent stages have a better peek at the information. So understanding how that information progresses and can be manipulated through those systems, I think, is a key aspect of the future of the field. But having said that, as Al always says, we have to keep in mind, and you've read that quote, so I'm not going to quote it again. I'm just paraphrasing, right? It's the same quote. But technology evolves, computational models change, new techniques and new methods are always developed, and they're always relevant to signal processing. One thing we should also keep in mind is that older techniques now become viable. So we should go back and discover them and see what those older techniques can bring back to the table. The Koopman operator I mentioned is, I think, from the 60s or even earlier. So it's very important to keep that in mind. And with that, I'm going to open it if there is time for questions. I also want to thank Al. He's been a great advisor, a great mentor, and wish him happy birthday and many more years.